Today's lecture is lecture 8. We'll be looking at acids and bases now. There's a few definitions that we can look at for acids and bases. The one that we'll be using mostly today is the Bronsted acid and base definition. And the Bronsted definition of acids and bases is very simple. Simply that acids are proton donors and bases are proton acceptors. Okay, so what exactly is a proton? Well, we know what a proton is when we refer to subatomic particles, right? Proton is in the nucleus, it's positively charged. And when we consider a proton, when we're talking about acids and bases, we are considering a lone proton or an H plus, right? A hydrogen ion that's positive, okay? If we think back to entry-level chemistry, we may have seen the Lewis dot structure for hydrogen, which is an H with a dot. Because hydrogen is number 1 on the periodic table, it simply just has one proton. So a hydrogen atom is one proton, and then it has one electron orbiting it, right? It's just one proton and one electron. That's a hydrogen atom. If we pluck off that electron and make it positive, all we're left with is a proton. Okay, so H plus is simply a lone proton. And a lot of acid-base theory, especially when it comes to the Bronsted definitions, we'll just be considering that H plus. Okay, so when we're considering acids and bases, what we're talking about is the movement of H plus or hydrogen. Something that donates an H plus will be a proton donor or an acid. Something that accepts the H plus, makes a bond to it, that's a proton acceptor. That'll be a base. So I have a generic formula here. I have an example and then a generic formula. So in the example formula here, we have HCl, hydrochloric acid, with water, H2O. And what we have here, these double arrows, they're single-headed arrows pointing to the left and the right. These we call equilibrium arrows, because most acid-base reactions are in equilibrium, meaning that both the forward and the reverse reaction are occurring together in competition. Sometimes they will be going at equal rates. Most of the time, they will be going at unequal rates. So sometimes the forward reaction will be preferred, sometimes the reverse reaction will be preferred, and sometimes they'll be equal, okay? If the forward reaction is preferred, we would put a larger arrow and then a smaller arrow for the reverse. And if the reverse reaction is favored, we would do the opposite, okay? We'll work more with these arrows as we go along, but for now, just note that these arrows pointing both directions means that these reactions are in equilibrium and they go back and forth, okay? It's not a single reaction going from left to right. So in this case, we have HCl, hydrochloric acid. Now, water in this case, and in many cases, as we'll see, can be a base, could also be an acid, okay? H2O could donate a hydrogen, right? It has hydrogens on it, could donate a hydrogen. And it could also accept a hydrogen by making a bond to it with one of these lone pairs. So hydrogen, it could be either an acid or a base. In this case, it's acting as a base since it's reacting with HCl, a strong acid, HCl. Okay? So if we look at this example, if we look at the products, now we have Cl minus and H3O plus, the hydronium ion, H3O plus. H3O plus, we can also put that lone pair on it. Okay? Good to include your lone pairs as you're learning. So what's happening here? HCl, hydrochloric acid, is losing a proton. This hydrogen here that I circled is no longer connected to chlorine. It's now connected to water, okay? So this HCl lost a proton. So if this HCl lost or donated a proton, this would be the acid, okay? In this example, that's the acid because it's donating or losing a proton H plus. The water is being a base because if we look at the products, it's now H3O plus. So the water has gained or accepted a proton. So the water is acting as a base. And then you may have seen the terms conjugate acid and conjugate base. So this is for the reverse reaction. If we consider the reverse reaction, the hydronium ion is losing a hydrogen, right? If we consider going from hydronium to water, it's losing a hydrogen. It's losing that proton, so it's a proton donor. So this is the conjugate acid. It's the acid for the reverse reaction. Conjugate acid, okay? Conjugate, spelled like that. I'm just abbreviating it, conj. Conjugate acid, and we also have the conjugate base here. Because for the reverse reaction, the Cl minus is gaining a hydrogen. It's accepting a hydrogen. So for the reverse reaction, Cl minus is the base. So we'll call Cl minus the conjugate base. Now we are going to use these curved arrows that we talked about. These arrows where I'm drawing curves from starting point to finish point. We use these in resonance to show the movement of two electrons. We're going to be using these for the rest of organic chemistry. Organic chemistry is essentially the movement of electrons, the pushing of arrows. So this is a very important skill. In acid base and a lot of the future chapters, we will be drawing these curved arrows to show reactions, to show how valence electrons are making new bonds and breaking new bonds, okay? So when we consider HCl, look here at HCl, we have a hydrogen single bonded to a chlorine. Now chlorine has 8 electrons, right? There's 2 electrons in that single bond. Hydrogen just has a 1s orbital, it just has 2 valence electrons, okay? So hydrogen is happy with 2 valence electrons, chlorine has 8 valence electrons, okay? When we consider the HCl bond, remember it's polarized towards chlorine, right? There's a dipole towards chlorine. What does that mean? That means that hydrogen is partially positive and chlorine is partially negative. So we have a partially positive hydrogen and a partially negative chlorine. I'm going to draw a water molecule over here. And we know what part of the water molecule is partially negative. The oxygen, the lone pair area up here, and these hydrogens are partially positive. Again, because of that difference in electronegativity, there's a dipole there. So this partially positive oxygen wants to react with, it wants to associate with this partially positive hydrogen, and it does so. This lone pair on oxygen can make a bond to this partially positive hydrogen. It's attracted to it, right? Because of differing opposite charges. So we have some interest, the oxygen has some interest in that hydrogen, and it can make a full bond with it. If it does, that would be an acid-base reaction. If this lone pair on oxygen attaches itself to this hydrogen, we've formed a bond. Now hydrogen can't have 2 bonds, so what does it do? It leaves behind the bond that it used to have. It says essentially to the chlorine, like, I have a new bond, a better bond over here. I'm just going to kick you out. Kicks off that 2 electron bond there, gives its electrons to chlorine, and that makes chlorine perfectly happy because now it has 8 electrons all to itself, right? It's a pretty electronegative atom. And hydrogen's just happy too because it has 2 new electrons. It has 2 electrons, so it's happy with its 2 electron valence shell. So these arrows here are very important. What we're showing is, I'm going to draw them in red, just highlight them. The lone pair on our base, in this case water, is forming a bond with this acidic hydrogen, this H. The hydrogen is leaving behind its 2-electron bond, and we're showing that with this small arrow here, where this bond is essentially popping off, breaking, and those 2 electrons are just ending up on chlorine as a lone pair. Over here on the products, I drew the lone pair in red. That red lone pair used to be a HCl bond. Now it's a lone pair on chlorine. Okay. And if we look at our product here, we see H3O plus over here in blue. We have oxygen with these 3 bonds to it now. Why? Because one of its lone pairs made a new bond to hydrogen. Okay. So that's very important to understand. I just summarized up where those electrons are moving in an acid-base reaction and what we mean when we say proton, hydrogen, acid, and base. Okay, so if you don't understand that, if that didn't make sense, rewatch it because it's very important to understand that base concept. Okay. We will get more practice, of course, as we go along. But here's just a generic acid-base reaction that I drew on the bottom. And so this could be anything. Obviously, I have an example up top with hydrochloric acid and water, okay? But it could be anything. And we abbreviate that with HA, meaning some acid that has a hydrogen on it, right? Because that's by definition what an acid is. It has a hydrogen that could be donated. So HA, meaning an acid with hydrogen, plus a base, B, and the base could either just be something with a lone pair, right? Anything with a lone pair, or it could be something that's negatively charged, as we'll see. It could be base with a lone pair that's negative. What do all Bronsted bases have in common? They have a lone pair. That's an important thing to remember. Bases will have that lone pair. Now, not everything with a lone pair is a base, but all bases have lone pairs. All Bronsted bases have lone pairs. Okay. So what does that give us? It gives us A minus after HA. After that hydrogen leaves, we're left with A minus plus a base with, I drew an A there. It should be a hydrogen. Plus a base with a hydrogen, BH plus. So the hydrogen, let me recircle that. So the hydrogen goes from the acid to the base to become BH plus, right? So this is just a generic formula here where we have an acid, we have a base, and then they essentially transfer ownership of that hydrogen, okay? Now, if we start with a negatively charged base and it takes a hydrogen, that means it would be neutral, right? That's something to remember. Make sure your charge is always balanced. If we look up to the example I drew up above, we have HCl plus H2O, both neutral molecules. And if they transfer ownership of a hydrogen, that gives Cl minus plus H3O plus. See how the charges balance out? We have a neutral and a neutral on the left, and then we have a negative and a positive on the right. So the charges balance out. Okay. Okay, so that's just like a brief overview of acids and bases. That's sort of what this chapter, what the next 2 lectures will be on. Now, let's talk a little bit, unfortunately, about math. There's not a lot of math in organic chemistry, which is why I decided to study it so extensively, because I don't like math. But there are some important underlying concepts that we should be aware of that require math to understand, okay? So we are going to just take a quick look at this equilibrium. Now, just a forewarning, the next 5 to 10 minutes as I talk about this. It's not 100% necessary for you to understand everything I'm drawing and explaining. But what I'm going to be doing is writing out sort of almost like a proof in math or derivatization. I'm showing why something is the way that it is, okay? Based on what we know so far for acids and bases, okay? Because I'm going to explain to you essentially how we can determine if something is a strong acid or a weak acid or a strong base or a weak base, okay? How acidic is something? How strong of an acid do we have? Okay. So when we consider some basic equation like this, let me draw it up top here. I'll draw a different generic equation. I'm going to draw one with water, HA. So we have an acid, right? A Bronsted acid, some acid with hydrogen on it, plus H2O, plus water. The equilibrium arrows, so this reaction goes back and forth. If we do an acid-base reaction between them, that would be A minus, because A, the acid is losing its hydrogen, it's H plus, the proton, plus H3O plus. The base, in this case water, is gaining a proton, gaining an H, so it becomes H3O plus. So there's our generic equation of water with some acid, some Bronsted acid. Now the equilibrium constant we call capital K EQ, the equilibrium constant. And this KEQ essentially tells us which reaction is preferred, the forward reaction or the reverse reaction, okay? And the KEQ is going to be equal to, hopefully this makes sense intuitively, the concentration of the products, H3O plus, and A minus, over the concentration of the reactants, HA and H2O. And I'll draw that out here with text also. So that equals the concentration of products over the concentration of reactants, okay? That's the KEQ. So think about it intuitively. If the concentration of the products is higher, that means the forward reaction is favored. If the concentration of the reactants is favored, that means the reverse reaction is favored. So if the forward and the reverse reaction are exactly the same, KEQ should be what number? If the numerator is the same as the denominator, we should have 1, okay? So for a equal reaction, or we'll call it a reaction at equilibrium, KEQ equals 1. Okay, so that's very important. KEQ will equal 1 when the reaction is at equilibrium. That means the forward reaction is the same as the reverse reaction, same rates, okay? Same concentration of products, same concentration of reactants. KEQ, the ratio of those two, is 1. Okay? Hopefully with me so far. Now what we are going to do is we're going to just rearrange this a little bit, and we are going to introduce this term Ka, which is just the strength of an acid. Ka is just the strength of an acid. Now, what we're going to do is we're going to set this equal to the KEQ of water, which is H3O plus and A minus over just HA. Okay, we multiplied both sides by water. Okay, so we call that Ka, or the strength of an acid. Okay, and so if we think about this, right, Ka, if we have a very strong acid, that means we have something that readily dissociates in water. Okay, that's a very important concept to know. When we have a strong acid, we have something that readily dissociates in water. I'll actually write that out also. It could be any other solvent as well, but water is just the standard that we use in chemistry, right? In almost all physical sciences. A strong acid readily dissociates in water, which means the forward reaction, when we draw out the acid-base reaction, is favored, right? If we have a very strong acid, looking up at our generic example on top, if we have an acid that is very strong, that means it has a hydrogen that is very willing to leave. It wants to be A minus, right? That hydrogen really wants to leave from the acid. So a strong acid will readily dissociate in water. A strong acid has that hydrogen that really wants to leave. So looking back at Ka, if we have a strong acid, what does that mean in terms of our equilibrium arrows? It means the products should be much higher. It means H3O plus and A minus should be much higher, because if we have a strong acid, it will readily dissociate in water, right? The forward reaction. A strong acid will favor the forward reaction. So what does that mean? Well, that means we can sort of gauge how strong an acid is by looking at the concentration of products over the concentration of starting materials. We can get numbers for Ka varying from about 10 to the negative 50 all the way up to about 10 to the 10. Okay, so these are all possible values, and we could have some outside of this range, but these are all possible values for Ka. We have such a wide spread of numbers, right? Where 10 to the negative 50 would be a very weak acid, and 10 raised to the 10 would be a very strong acid. If we have a Ka that's 10 to the 10, that would be a very strong acid. Again, because a strong acid will favor the formation of the products, H3O plus and A minus. Okay, so this would be the range of Ka values that we look for, but obviously we don't want to use these numbers because they are huge, right? We don't want to work with these big numbers. So what do? Well, we just take the negative log of the Ka. And remember, when you take the logarithm, you essentially take this exponent, turn it into a base number. And if we take the negative of it, we just simply switch the value. So what we're doing here is we take the negative log of the Ka, and this gives us a new value, which is the one we're after all this math, which is the pKa, lowercase p, capital K, A. And this is the good one we're looking for, the pKa. It's the negative log of the Ka, which is the strength of the acid. And we're just taking the negative log just to make it an easier number to work with. So our pKa values will go from about negative 10 all the way through to about 50. And we could go outside this range. This is just what we'll be working with in this class, where negative 10 is a very strong acid. and 50 is a very weak acid. Okay, so both pKa and Ka are ways to represent the strength of an acid. We are going to be using pKa to represent the strength of an acid because we want to work with simple whole numbers like -10 to 50 rather than numbers like -10 to the -37th power. Okay, we don't want to have to write numbers like that. So we just take the negative log of it just to make it more easy to represent. And so this pKa value is going to be our numerical value representing the strength of an acid, representing how readily it will dissociate in water, okay? Representing the strength of that forward reaction, okay? So if you didn't follow much of the math, that's okay. Just understand that pKa is our numeric representation for the strength of an acid. It'll typically be between -10 and 50, where -10 is a very strong acid, 50 is a very weak acid, and it can be anywhere on that range. Okay. What we're going to do next is I'm going to draw out a bunch of acids and bases, a bunch of molecules, and give us an idea as to some of these pK values, what they mean, and which ones we should know. I by no means want you to memorize all of these values, but it's good to at least know a few standards in your head, okay? Okay, so here's a chart that I drew with some of the more common pKa's and probably some pKa's that we should know. I'll circle the ones that you definitely should know, but I think this chart of, what's this, about 9 pK values, I think these are good ones to know because we can use them to infer the pKa's of similar looking compounds if we know these, okay? So this is sort of a nice good spread ranging from -9 up to 50, where we can get an idea of what are some strong acids and what are some weak acids. And inversely, what are some weak bases and strong bases. Remember, a strong acid, the conjugate of a strong acid is a very weak base. So just looking at our first example, H2SO4, sulfuric acid, it's a very strong acid, has a -9 pKa. Remember, very low pKa numbers, negative pKa numbers are very strong, and high pKa numbers are very weak acids. So sulfuric acid is a very strong acid, which means the conjugate base, HSO4 minus, is a very weak base. A very strong acid has a very weak conjugate base, okay, and inverse. A very weak acid has a very strong conjugate base, okay? So just really quickly, when we look at these pKa numbers, we need to remember over here on the left, pKa units are orders of magnitude because it's a negative log of the Ka, which is the true strength of the acid, the Ka. We're just taking the negative log to make it a nice number to work with, but each number difference, as we change incrementally the strength of the acid, each number represents an order of magnitude because this is the exponent of the Ka, remember? So one pKa unit is one order of magnitude difference. That means if we compare something that has a pK of 10 and a pKa of 16, that means that this pKa of 10 here is 1 million times more acidic. Okay? It's 6 pKa units lower, right? 10 compared to 16. And each pKa unit is an order of magnitude difference. Therefore, something with a pKa of 10 is 1 million times more acidic than something with a pKa of 16. Okay? Just to give you a frame of reference. Okay, so looking through our list here, let's talk about these acids and bases and just work our way down. We've already talked about sulfuric acid there, H2SO4. It's a very strong acid with a pKa of about -9. Okay. The conjugate base, if we took off the hydrogen, we'd end up with HSO4 minus. That conjugate base is a very weak base. Well, first off, I didn't draw any lone pairs on any of these structures. If you want to fill them in as practice, feel free, but I feel like we're pretty comfortable with them, and I didn't want to clutter this already cluttered chart here. So thinking about a very strong acid, very weak base like sulfuric acid, one way that I think about this is that H2SO4, if we consider the hydrogen in red, now either of these two hydrogens could come off, but let's consider this one in red. That hydrogen, if it's a very acidic molecule, H2SO4, that red hydrogen really wants to leave. It really wants to dissociate. That's what it means to be a strong acid. It means that that hydrogen wants to leave, wants to be donated, right? If it does, that makes the HSO4 part of the molecule nice and happy. It thinks to itself, we finally got rid of that red hydrogen, and it's happy again. So when we consider HSO4 minus the conjugate base here, it doesn't want to take that hydrogen back. It really doesn't want it back. It doesn't want to act as a base, right? Remember, a base accepts hydrogens. HSO4 minus up here on the top right, it does not want to accept another hydrogen. Therefore, it's a very weak base. So when you have a very strong acid, it means that you have a very weak conjugate base. Okay. The next molecule I drew here is the hydronium ion, H3O+. This will be very common, right? Because water, you'll see in a lot of examples. When we consider H3O+, it's a strong acid, has a pK of -1.7. This is definitely one you should know. -1.7. That means that any of these three hydrogens on H3O+, they're all equivalent, right? They could leave, any three of those could leave, act as a proton donor, and you'd end up with H2O, which would be the conjugate base. And the strength of that acid, -1.7. It's a strong acid. The next example I drew here is acetic acid, right? That's the component in vinegar. Acetic acid, first off, this functional group, when we have a carbonyl, a C double bond O, attached right to OH, to an alcohol, when they're together on the same carbon, we call it a carboxylic acid. And it's known to be a very good, strong acid with a pK around around +4. Why is it a strong acid? Well, because this negative charge, if we look at the conjugate base, that negative charge is quite stable. Why is that negative charge quite stable? Because it's partaking in resonance with the carbonyl next door, right? See how we use resonance there? This is a stable negative charge because it's participating in resonance. Therefore, if we had a hydrogen attached to that oxygen, it's a relatively acidic hydrogen because it doesn't mind if it leaves or not, right? This hydrogen, perfectly fine leaving, because if it does, it leaves behind a good, stable negative charge. Okay? So there's acetic acid, pK around 4. Water is obviously one we should know. That's going to be very common. Water has a pK around 15.7. 15.7. If we took a hydrogen away from water, if water acted as an acid, we would end up with OH minus, the hydroxide ion. Okay. And this is sort of, right in the middle of our chart here. Water could be an acid, could be a base, depends on how we use it. Okay, depends on what other reagents are in the system, but 15.7. Now we can use this information to infer the pKa of something like an alcohol. I drew 3-carbon chain over here with an alcohol on it, propanol. We can infer the acidity of propanol based on our knowledge that water is 15.7. Water is very similar to this alcohol, right? It just has a CO bond instead of a OH bond there. But propanol and the other alcohols will be in the neighborhood of 16 to 18, very similar to our 15.7. Okay, that's why it's important to know some numbers, because if you memorize pKa of water as 15.7, then you don't really need to memorize the pKa's of alcohols, because you know alcohols are just like water. Okay. Next on the list here, we have acetone, just a 3-carbon chain with a carbonyl. We can take off one of these hydrogens next door, right? We have 3 hydrogens on those methyl groups that I just drew there. We could pluck off any of those hydrogens and make a negative charge at that position. That negative charge is stable because it's partaking in resonance. That has a pKa around 19.2. And then I'm going to look at ammonia first, and then we'll talk about the carbons. Ammonia, NH3, if we took off a hydrogen there, it would then become NH2 minus. Okay, so if ammonia is acting as an acid, its pKa would be around 38. And then we have the 3 carbons, the 3 different types of carbons. We have our sp3 carbon, our sp2 carbon, and our sp carbon. If we have an sp hybridized carbon, a triple bond, that hydrogen is the most acidic of the 3 with a pKa around 25. Definitely know that one. If we have a double bond, right, a C double bond C with a hydrogen, that pKa is much higher, around 45. And a simple sp3 carbon is around 50. It's very weakly acidic. The CH bond is quite stable. Both parties are happy. That hydrogen is not interested in leaving whatsoever, but it can under some circumstances, okay? If it did, if we took off a hydrogen from an sp3 hybridized carbon and we ended up with a negative charge on carbon, that's a very strong base, right? Because it has a very weak conjugate acid. Okay, so definitely know these circled values, definitely know those, but I think it's good to know this whole chart. Okay, we'll use this chart to do some practice problems. And then we'll talk more in depth about why these pKa values are as they are, and talk about how we can infer qualitatively the strength of an acid without using pKa values. Okay, so let's look at just a couple practice problems here before we wrap this lecture up. We'll continue our discussion in the next lecture on acids and bases. But just to finish off today, let's consider that pKa chart we just drew out to consider which of these pairs has the stronger acid or the stronger base. Okay, so if we consider our first one here, we have a carboxylic acid and we have a hydronium ion. Now, a very easy and simple way to determine our stronger acid is to consider the pKa values. So let's refer to that table, refer to that chart to get some values here. A carboxylic acid has a pKa around 4, and the hydronium ion is around negative 1.7. We know that a lower pKa number is a stronger acid, so therefore the hydronium ion is a stronger acid than this carboxylic acid. What about if we compare ammonia to water, NH3 versus H2O? Well, ammonia has a pKa around 38, and water has a pKa, hopefully we remember off the top of our head, as 15.7. The lower pKa is more acidic, which means that water is more acidic. What about the base strength? Now, is there such a value as pKb? the strength of a base? Yes, there is, but acids and base have an inverse relationship. It's not necessary for us to use pKb. It's sort of redundant because we can simply get along using just the pKa values. So we don't really talk about pKb as the strength of an acid, although it is something that does exist. It's not used. We can simply compare the pKa's of these conjugate acids. So if we look at the first example, let's just take the pKa of the conjugate acid, which is the triple bond. That's around 25. So we'll assign that a value of 25. Well, let's put the 25 over here because it's really this, right? The triple bond there that has a pKa of 25. Ammonia has an anion, NH2 minus. Let's take the conjugate acid, which would be NH3. NH3 pKa is 38. So our stronger acid is the triple bond, which means the triple bond is a weaker base. Remember, there's an inverse relationship between the two. So NH3, this one right down here, is a weaker acid, which means that as a base, NH2 minus is a stronger base. Remember, weak acids are strong bases, and strong bases are weak acids. Okay, it's sort of tricky because there's two inverse relationships. pKa values increase inversely with acid strength, right? As you increase the pKa number, you lower the strength of the acid. And acids and bases themselves have an inverse relationship. A strong acid is a weak conjugate base, and vice versa. So make sure you get those inverse relationships squared away in your head. Looking at our final example here, we have a carboxylate ion. We have a carboxylic acid that has been deprotonated. So we have this negative charge that's left here. We can throw on some lone pairs if we want. Each of these negative oxygens has 3 lone pairs. And we're comparing that to propanol, which has been deprotonated. Okay, so the anion of propanol, this negatively charged oxygen. Let's look at the conjugate acids of the two. I'm going to draw them actually right above just to make some space. So let's consider the conjugate acids of these two, and that'll tell us how strong they are. So the conjugate acid of the first molecule would be this, which has a pKa around 4. And this propanol, which has been deprotonated, if we add that hydrogen back, we'll have the 3-carbon chain with OH. An alcohol, if we consider water at 15.7, alcohols are typically around 16, 17 range. Doesn't really matter whether we put 16, 17, 18. Either way, this molecule on the left is much more acidic, right? This is more acidic or stronger acid, which means it's going to be a weaker base. So what's our stronger base? Our stronger base is the weaker acid, which will be this negative charge here, the oxygen which has been deprotonated from propanol. Okay. So we can use pKa not only to determine the strength of an acid, but also determine the strength of a base. Okay, so although pKb does exist as a term, we just don't use it. It's not necessary. Okay. So those are some examples of how we can use pKa as a quantitative solve for a lot of these problems. Next lecture, we are going to look at a more qualitative approach where we can determine acidity qualitatively by looking at and analyzing the molecule and how everything is attached. So we're essentially going to have 2 different ways to solve problems, acid-base problems. We can use pKa. If you remember your pKa values, you can use those, which is probably a more simple approach if you can memorize them. Or we can use the qualitative approach, which we'll look at next time. Both are just fine. Neither one is better than the other, but whichever one is better for you, you can use. Okay. Okay, that's everything for this lecture. I will see you in lecture number 9, where we will finish our discussion on acids and bases.